Hello. So this video is focused on an introduction to probability. We don't actually go through all of chapter 6. We just brush the surface at understanding some very important vocabulary words and some important aspects to the basic notion of probability. But for this particular course, we don't go into any heavy lifting and talking about conditional probability or anything like that. Okay, let's get started. So, a random experiment is defined as an activity or phenomenon that meets the following conditions. There is one distinct outcome for each trial of the experiment. The outcome of the experiment is uncertain, and the set of all distinct outcomes of the experiment can be specified and is called a sample space. Okay, and we typically denote that by S. So these definitions probably make no sense until we dive into some examples. Okay, two more words before we get into the example though, is an outcome is any member of the sample space, and an event is the set of outcomes. Okay, again, it'll make a little bit more clearer when we define these out. So for example, if we're taking a look at a survey that consists of asking people their blood types, we know that the different letters on the blood types is O, A, B, and AB. And there's also a positive and negative that are attached to these blood types, which makes them completely different from each other. So when we are determining the number of outcomes and identifying the sample space, we first have to decide what are the possible combinations for outcomes, and all of those individual outcomes create the sample space. So using a diagram tree like this one is a great way to map out and organize all the different types of outcomes in a particular random experiment. So here we would say, well, first someone would tell me whether they were O, A, B, or AB, and then they would specify whether it's O positive, O negative, and so on, giving us each one of these branches of the tree is an outcome of the probability experiment. And when we put all the outcomes together and list them, that's what's defined as the sample space. So if an experiment is performed n times, that just means a finite number of times, under identical conditions, and the event A happens k times some integer k, the relative frequency of A is given by the following expression. And we've calculated relative frequency before, so this is no different than when we learned about the frequency tables in chapter 3. So the relative frequency was always calculated by the part divided by the whole. So that's literally all this is saying, and relative frequency is no different from a basic probability calculation. So if we ran a survey on your favorite color, for example, and I found out that 34 people out of the 100 that I asked liked pink, then I can calculate the relative frequency, which would be 34, the amount that liked pink, divided by the total number of people I asked, 100, and I would calculate my relative frequency to 0.34. That is also known as the probability or the likelihood that when asking a random person, the probability that they will say that pink is their favorite color is 34%. The experiment, let's take a look at this example. So let's define the experiment as tossing a coin and observing which side of the coin appears on top. The duration of the experiment is tossing the coin 1,450 times, which gives us a sample size of 1,450. Observe the event getting ahead. Okay, so then we look through our results of the 1,450 tosses, and we identify that 718 of those tosses were heads. And then we calculate the relative frequency, also known as the probability that we would expect tossing a heads. And no surprise, the value comes out to close to 50%. As we know, the classic probability of tossing a coin and getting a heads, one toss at a time, is a 50% chance. As the number of repetitions of an experiment increases, the relative frequency of an event tends to approach the actual probability. So, what do we mean by that? What we're talking about is the law of large numbers. So, if you had a coin in your hand right now and you tossed it 10 times, how likely would it be that exactly five, half the number of tosses are heads, and exactly five, half the amount of tosses are tails? Honestly, it's probably unlikely. You would toss 10 times and you might get eight heads and two tails. You might get all heads or any combination of the possibilities. So uh, when we repeat an experiment a low number of times, we may not be concluding the proper probability because of confounding variables, because of the way we toss the coin, so human error. Did we flip it flip the coin, catch it, flip it over onto our hand every single time? Did we accidentally drop it one time and it's rolling away from us and we go and stomp on it to stop it from rolling? Did we use the exact same coin, a penny or a quarter or a dime? So there are many different things as humans that we can do to affect an experiment. Um, and in general, in any experiment, there's always those confounding variables that we discussed in earlier sections. So the best way to alleviate those from affecting our results is by repetition. And if you look at this graph here, you can see that if I tossed a coin from 0 to about 20, 30 times, I'm seeing a large variation in the data. So I'm seeing that sometimes heads is 80% of the time, and sometimes it's only 30% of the time. And that's because it's such a small sample size. But the moment that I expand my sample size to over 100, I am noticing that the variation is reduced greatly, and I am hovering around the actual probability of tossing a coin and getting a heads, which is that 0.5 or 50%. So this is called a classical approach to probability. So a classical probability is when you take the count of desired outcomes, like getting a heads, divided by the total number of times you attempted to get that outcome, and you get what we call a classical probability, or exactly the same calculation we did with relative frequency. Now, it's really important to mention that in order for classical probability to work, we need to make sure that each outcome in the sample space is equally likely to occur. That's really important for the classical approach. So for the coin, we know the classic probability of heads versus tails are both 50-50, which is why flipping a coin is a classical probability. Rolling a six-sided die, each one of the numbers on the six-sided die, every time I roll the die, there's a 1 out of 6 chance for any one of those sides to be on top. That would also be a classic probability. So again, a coin was tossed 3 times and the number of heads was observed. The sample space consists of these 8 possible outcomes. So these are all combinations of 3 tosses between heads and tails. Let A be the event of getting at least one head. What is the classical probability? Well, if we look at our sample space, there's only one in the sample space that does not include at least one head. Therefore, there are 7 that do include at least one head. And that's where we get this result down here where we say, okay, there's a count of 7 possible outcomes out of the sample space that include at least one head out of the total 8 possible outcomes, leaving us with 0.875, or if we translated that to what we would speak in English, we'd say there's an 87.5% chance that when tossing a coin 3 times, you would have at least one head. Another good example, we roll that die and observe the number of dots on the uppermost surface. So essentially you roll the dice and it's the top surface, which is what we're used to if we're working with a die. Let A be the event of observing an even number. What is the probability of an even number being on the top of a rolled die? Well, if we think about it, there are 6 sides to the die. 3 of those sides have odd number dots, and 3 of those sides have even number dots, 2, 4, and 6. Therefore, there are 3 possible outcomes out of the 6 in the sample space that will be even. And there's a 3 out of 6 chance, or 0.5, a 50% chance that we will roll an even. Okay, that's all part of the solution we just discussed. Another type of probability is called empirical or statistical probability. And this will be conducted through things called simulations, where you have to repeat an experiment that you are simulating to get results, or any type of experiment really where the outcomes are unknown. So, for example, driving up to an intersection, stopping at a traffic light. I want to know, what is the probability when I roll up to the specific intersection and traffic light at 8 a.m. in the morning? What's the probability the light will be green? Well, it's not a 1 out of 3 chance, even though there's 3 light colors on the traffic light, green, yellow, and red. It's not a 1 out of 3 chance that it's going to be green. And logically, we know this because the yellow light is not on the same amount of time as the green or the red. So we can assume that they are not equally likely to occur. The only way to really calculate this probability of a green light at 8 a.m. would be to conduct an experiment. I roll up to that light every morning for a month at exactly 8 a.m. and record my observation of what color the light is. Then, out of the, let's say there's 30 days in the month, then out of the total 30 observations making up the entire sample space, I would count how many of those observations were indeed green. Then I would take the count of green divided by the 30 days that I collected observations to calculate a empirical probability on what I would expect the probability would be for the light to be green at 8 a.m. Another example, a company is conducting an online survey of randomly selected US adults to determine how they read books during the past year, if at all. So far, 1,490 adults have been surveyed. The pie chart that we have here shows these results. And we want to calculate the probability that the next adult surveyed would read only print books during the last year. So in order to do that, we know that there is a total of 1,490 observations. We would then go to the results of the survey, and our focus is read only print. So read only print, there were 578 responses that stated they only read print books. We then take that part, the 578, and we divide it by the whole, all the people asked, the 1,490, and we create a relative frequency, also known as a probability, that the next person asked would say that they only read printed books, which is a 0.388, or as we would translate that in English and state, it's a 38.8% chance that the next person I survey out of this same population would state that they only read print books. Okay, we really should understand the range of the probabilities. So probabilities only exist between 0 and 1. There are no negative, and there are none bigger than 1. So 0 means that it's absolutely impossible, it's not going to happen. And 1 means it's absolutely certain. There's a 100% chance it's going to happen. I think that's one of the most things that annoys me about the Weather Channel, is because when they say it's a 100% chance of rain and then it doesn't rain, they're probably the only career in the world that can get paid so much to be wrong more than they are right. But that's the weather for us. So notice the scale, 50-50, 0.5 is an equal chance between the items. 50-50 is typically talking about 2 outcomes. But anything that's between 0 and 0.5 is more of the unlikely range of an event occurring, and 0.5 to 1 is more of a likely range of an event occurring. Other things that we need to consider is the definition of what we mean when we talk about a simple event versus something that is not simple. So a simple event consists of a single outcome. So if my goal is, here's my experiment defined as tossing a coin and then rolling a die, and I am specifically focused on a heads and then a 3, that's a simple event because my desired outcome is one outcome out of the entire sample space. But if I say that I just want it to be heads and an even, well, there's actually three possible outcomes for a heads and an even, and therefore that event would not be simple. Okay, determine the number of outcomes in each event and then decide whether each event is simple or not. So an example, for quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. Now, this wording here is what really tailors us to a simple event. And that's because it's saying that out of all these defective parts, you're only looking for one specific one. So that means that there's only one specific outcome that is a desired result, and making this event simple. In this example, you roll a six-sided die and you have defined the result, what you're looking for in your probability experiment, as being rolling at least a 4. Now, translating this type of terminology, at least, can be tricky. I find that what helps is if I think about money. If I tell myself I have at least $4 in my pocket, well, I know that that means that I know I have $4, but I might get lucky and find more. I don't know if you guys ever experienced that where you're doing your laundry and you randomly find a 10. Love that stuff. But thinking about money does help me translate this, that at least a 4 is talking about the upper half. So 4, rolling a 4, a 5, or a 6. Since there are three possible outcomes with this defined event, it is not simple. Okay, that is our basic introduction to probability. And this concludes our video.